Professor Clements with you again in Chapter 19, Sections 2 through 4 in the OpenStax College physics textbook. And talking now about electrical potential in connection to a uniform electric field. So here we have a drawing with a uniform electric field. That means that the electric field has constant magnitude here, here, all the way across, and constant direction. When that is the case, we can calculate the potential difference between two locations with a calculation of E volts per meter times the distance between the two locations. So potential difference equals electric field multiplied by the distance between the two locations. So perhaps it's, let's say for something easy here, 2 meters. 2 meters across from inside edge to inside edge in this geometry. What would the electric field be? If we could rearrange this, the electric field would be the potential difference divided by the distance. So we would have 100 volts. That's our potential difference when we have 100 and 0. And we have 2 meters across here. I'm just inventing 2 meters. So we'd have 50 volts per meter would be the strength of our electric field. It is important to emphasize that when we're doing this calculation, the electric field must be constant and the electric field must be just in one direction that we're moving along for our distance. So that's just a short discussion there. That's the main point in section 2, is a relationship between potential difference and electric field and distance. Notice also in here that where the electric field lines cross a line of equipotential, we've got a right angle. 75 volts all the way along this line, 50 volts through the center, 25 volts along this line, and also drawing the electric field at a conductor, we have a perpendicular arrangement of the surface of the conductor and the electric field line. Now let's back up to, if I can activate my PowerPoint here, back up to a single charge Q. The blue lines with the arrows are the electric field lines. The green lines are lines of equipotential. And we can calculate a potential, a single potential V here is the meaning of this V, with KQ over R. And it's not R squared, just KQ over R is how we would calculate the value of electric potential at one particular spot. K doesn't look very good here. That's getting a little better. So on this inner circle, there's a certain distance R there. There's an R out here. There's an R out here, and these are all the same values of R. So around this circle, this first circle, the voltage is going to be the same. The electric potential is going to be the same value. As we move further out, our potential is going to be lower as R gets bigger, and out here lower still, out here lower still. And if we would go out to infinity for the value of R, what would the potential be? As R gets bigger and bigger and bigger, K and Q are fixed numbers, and hopefully you're guessing that the potential at infinity has a value of 0 volts. And all these lines in this example would have positive potentials because Q is positive. If you put a negative charge here, then do these calculations and draw these lines, they would all have a negative potential. So this potential can be positive or negative depending on the sign of the charge. If we'd have 2 charges in a situation, then we can add up their potentials. We'll go this one. Add up their potentials, and In this region, these green lines are positive. This charge dominates here. Its R values are smaller compared to the R values back to the negative charge. Over here, the potentials on the left would be negative numbers. A crucial thing, an important thing here, when we find the net potential at a point in space due to multiple charges, we simply add up the values of the potential. There are no components. The potential is a scalar, not a vector. So it's easy to add up potentials. You don't have to draw right triangles. You don't have to use sine and cosine. The value of the potential, the net value, is just adding up the potentials created by each charge. Again, notice that the electric field is crossing at a right angle to the lines of equipotential. And the electric field line starts on a positive, ends on a negative. The equipotential lines do not start or end. They are a complete path. The electric field lines start and end, but the lines of equipotential are a constant path. So we have that arrangement for drawing. And if we do another one here, two negative charges, and the net potential has been calculated. I have a question for you. Suppose we take a charge, start it right here on this line of minus 5 volts of equipotential, and I go out to here. I move the charge over to this location, again on the minus 5 line of equipotential. How much work would be required to do this, to move the charge along there? And the work would be 0. Because we're moving along an equipotential, the difference in potential is 0 volts. Work is Q times delta V, the change in potential. And when we're moving on an equipotential, there's no work required. It's only when we move in the direction of the electric field or against the electric field that there would be a non-zero work. Notice too, we've got the negative charges in the middle of these circles. As we go further away, the potential is coming towards 0. As R gets bigger, whether we have a negative or we have a positive, the potential heads towards 0 in that increased distance. If we want to figure potential energy, we could do so when there are two charges, and we do so with K, Q1, Q2 divided by R. That's the potential energy. It's different than the force. The force is K, Q1, Q2 over R squared. The potential is K, Q1, Q2 divided by R. It would be the potential energy. So you ought to read through the reading guide and see what other questions you might have, and ask your instructor some questions. But that's where we're going to finish. That finishes Chapter 19, Section 4. And we'll just stay tuned for other episodes.